I want to look now at some properties of the Fourier transform. These are properties that are really useful when you're computing with Fourier transforms that help you simplify the calculations that you're doing with transformed functions. The first one is really simple. It's linearity. The Fourier transform is linear. So this means if you have two functions and you add them together, the Fourier transform, the sum, is the sum of the Fourier transforms. It also means if you have some function like f of t, the Fourier transform of a, some constant a times f of t, is just a times the Fourier transform of f of t. So, for example, here we have a sum of a Gaussian and a constant. The Gaussian here is multiplied by some constant a. The Fourier transform is the sum of the Fourier transforms of these individual functions. A second property is scaling and coordinate reversal. These two are closely related, as we'll see. So scaling, what I mean here is that rather than just, if we have some function of x, if we multiply x by a, so we're scaling the coordinate by some factor of a, then the Fourier transform is also scaled. In the frequency or Fourier domain here, which is k, going from x to k, the k coordinate is scaled by 1 on a, and the magnitude of the Fourier transform is scaled by 1 on the absolute value of a. So for example, if we have a Gaussian here where the x-coordinate here is scaled by a, then the magnitude is scaled by 1 on a, and this k up here is scaled by 1 on a, which gives us a factor of a squared here, along with this 4. Now we can also choose this constant a here to be minus 1. In this case, we have coordinate reversal. So f of x becomes f of minus x, and this becomes the Fourier transform function, capital F, of minus k, or in time coordinates, f of minus t becomes the Fourier transform, capital F, of minus omega. The scaling out the front here is 1 on the absolute value of a, so we do not pick a minus sign up out the front here. We just, if you reverse the coordinates in real space, you reverse the coordinates in frequency space without any extra scaling factor out the front. It's also very useful to know about the symmetry properties of the Fourier transform. So the Fourier transform here is written with this kernel e to the negative I omega t, but this kernel can be expanded as a cos omega t minus I sine omega t. Now the cosine function here is even, and the sine function here is odd, and this gives us some particular symmetry properties of the real and imaginary parts of this integral. So, if f of t is a real function, then f of t times cos omega t is all real. And the integral of f of t times cos omega t will be an even function because the cosine omega t just picks out the even parts. And this happened also for the Fourier series, if you remember, when we expanded even functions in the Fourier series, we had only cosine components. So the real part of this entire integral will be the even parts of the Fourier transform. The imaginary part here has the sine function in it though, so the imaginary part of this integral will be odd, because the sine function is odd. So if f of t is real and even, then the Fourier transform will also be real and even, because the odd part will be 0. And if f of t is real but odd, then the Fourier transform will be pure imaginary and also an odd function. The next property I want to describe is known as duality, and this is just a fancy way of saying that the Fourier transform is almost its own inverse. If you look at the definition of the Fourier transform, you can kind of see this. The Fourier transform from x to k is defined with the kernel e to the negative I kx. The inverse transform from k back to x looks pretty much the same, except we've changed a sign up here in the exponent and accumulated a factor of 1 on 2 pi out the front. This is the same transforms written out with omega and t, in case you prefer looking at them in that way. Okay, so the only difference between the forward and reverse transforms is the minus sign and the factor of 2 pi. Now, to state the obvious, if you take the forward transform of f of t, you get big F of omega. Then, if you take the inverse transform of big F of omega, you get back to f of t. That's the whole point, and this is a way of expressing these definitions in words. Now, let's do a little thought experiment. What if you mess up, and instead of taking the inverse transform, you just keep taking the forward transform? So this transform here, or this one here, in terms of omega and t. So what I mean by that is if you take the forward transform of f of t, you get big F of omega. Now what if you take big F of omega and change the omegas back to t's, and then take the forward transform again? When you take the forward transform of big F of t, you'll get back to the function little f, but now little f will be little f of minus omega with a factor of 2 pi out the front. And the reason why you've got a sine here and a 2 pi here is that instead of taking the inverse transform, you've taken the forward transform again. So you've got a factor of 2 pi here wrong and a sine wrong from the kernel. But the important thing to realize is that the functions little f and big F here form a Fourier transform pair. If you start off with a function little f and take Fourier transforms or inverse Fourier transforms, any combination of them, no matter how many times, you always bounce backwards and forwards between the functions big F and little f with scalings of 2 pi and negative signs and changes of variables from t to omega or x to k, but you always have this pair of functions that follow each other around. So if you keep taking the transform, you bounce backwards and forwards between the function little f and big F, give or take factors of 2 pi and minus signs. And so the duality means that Fourier transforms always come in pairs. This is a really useful property, and I'll demonstrate it with, or explain it, I think it's easier to understand with some pictures. So let's use the notation here for a top hat function or in terms of time with width tau. And we know, because we've calculated, that the Fourier transform of this function is a sinc function. So in pictures, if we start off in real space with a top hat function, and just ignore all the factors of 2 pi and all that messy stuff, in real space we have a top hat function, in Fourier space we have a sinc function. But if we'd started with a sinc function in real space, duality tells us that the Fourier transform of this must be a top hat function, because Fourier transforms travel in pairs. If the Fourier transform of top hat function is a sinc function, the Fourier transform of sinc function is a top hat function. So we know now that we have these Fourier transform pairs, but we can use this duality property not just to know intuitively how these pairs look, but also get rigorous, mathematically correct Fourier transforms without doing any integration. So let's compute the Fourier transform of a sinc function using the duality principle. We haven't formally computed that Fourier transform. We know that it's going to be a top hat function, but we don't know what the factors of 2 pi are going to do. So let's get that right using the duality principle. So the Fourier transform, let's take the Fourier transform of sinc capital omega on 2 times t. Now we want to make this sinc function here look exactly the same as we have it here to make the duality function easy to use. So we'll multiply by an omega inside and take a factor of 1 on omega out the front here, which we can do through the linearity of the Fourier transform. So now we have omega sinc omega on 2 times t, and this looks exactly the same as this sinc function, replacing tau with big omega and t with little omega. So using the duality principle, we get that the Fourier transform of this must be 1 on omega times 2 pi top hat of negative omega on big omega, which we can simplify a little because this function is even, so the minus sign here has no effect, and we get this function here. So it's a top hat function because we know we know it has to be a top hat function, but now I've got the factor of 2 pi correct as well. And we can make a substitution here that big omega is 2 on tau, if we wish, and then we get that the Fourier transform of sinc t on tau is pi tau top hat little omega tau on 2. And so we've computed the Fourier transform of a scaled sinc function using the duality principle, not actually having to integrate anything. So what this is telling you is once you've computed the Fourier transform in one direction to get the transform function, you don't then have to go and compute the transform explicitly to get the transform of this function. You can figure out using the duality principle. The next feature of Fourier transforms is the coordinate shift property. So supposing we have a function here which we offset by some value x0, the Fourier transform of this offset function is just the Fourier transform of the function without the offset multiplied by a complex exponential e to the negative I k x0, where this is the offset here. There's an offset theorem for the other direction where you have a function which is now multiplied by a complex exponential with some offset here k0, and in this case you get the function f of k minus k0. So there are kind of two theorems here. One, we have a function offset by an amount x in real space, and another one we have a function f of x, which is multiplied by a complex exponential with some offset k0, that gives you an offset function in k-space. As an example, here is a Fourier transform of an offset Gaussian function. It gives you the Fourier transform you expect for the Gaussian with an e to the negative I omega a, where a is the offset here.